Okay, so let's consider some situations where we are not, or an object is not on a flat surface. And the infamous problem is what we call ramp problems. The infamous type of problem, I'm sorry, is what we call ramp problems. So let's take the two extremes, and then let's get to the intermediate, which is a ramp. So in this first example here, case one, I have an object, it's on a flat surface, and in this particular case, if I do the free body diagram, I hope it's easy to see that, of course, we have gravity pulling downward, and we have the normal force, which is the ground, pushing back on the object. And in a lot of these cases, it's pretty easy to see that the normal force and the gravitation, they're going to cancel each other out, assuming we are just resting on the table, right? That we, maybe we have some pushing sideways, but if there's no other real forces acting on this, it could be assumed that summation of the forces in the y direction equals 0, and that would mean that the normal force and the gravitation, they would cancel each other out, and if you rearrange it algebraically, the magnitudes of each would be equal but opposite, right? So, or the magnitudes would be equal. The directions are obviously opposite. Now, that's case one. You're as we've been doing. Case three is a weird case. So imagine you take the object and you put it on a surface that is like a wall, right? Take an object and try to put it against the wall. Well, if you put it against the wall, or if you have a very, 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 very tilted surface, gravitation is downward. And, there might be some scraping of the object against the wall, but that's not a normal force necessarily. If it's scraping as it goes down, it could be a little bit of a friction, obviously. Or maybe, it's barely scraping at all, and maybe the friction is even, really, really close to 0 newtons. There is nothing keeping, if you just put it against the wall and let it go, there's nothing keeping the block, pressed against the wall. Nothing. Especially if it's a complete vertical surface. And so in these particular cases, and we could even be really, 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 physics-y here and say that, the wall is very, very, very slippery. So maybe there's not even any friction. And we will, if I can erase this, it'd be great. I'm probably going to erase everything. All right, I'll do that. Yeah, so if we said the wall has no friction, there wouldn't even be that rubbing force, that frictional force. So in that case, we can say that there is no normal force because there is nothing saying it's going to stay against the wall. And so basically, if I put this against the wall, I can say it's basically, especially if it's a slippery surface, I can pretty much say it's free fall, right? I hope that makes sense. So there's no normal force here, or it can be assumed that it is so small it's negligible. Now, in case two, in a ramp situation, well, we're kind of in between here. Again, gravity is acting on us, but again, gravity always acts straight down. Let's see. Okay, so gravity acts straight down. Now, normal force acts between the surface and the object, but it's always perpendicular to the surface. And if that's the case, that normal force has to be here, perpendicular to the surface. That's very important. that 90-degree angle has to happen. And so if I, and this again, a normal force, okay. So if we do this, and I make the free body diagram the way it should be, I take this arrow and I put it where it needs to be. And I can get rid of that 90 degrees because we knew that should have happened. So here, my normal force is not straight up balancing my gravity at all. And this creates a situation where the normal force is in a quadrant, right? If we typically think of X and Y coordinate system as, you know, this way and this way for positive Y and positive X, well, that means normal force is now in the first quadrant, the way I have it drawn. And that means the well, what does that mean? What does that mean in terms of the balancing, the gravity, and so forth? And the other thing to ask yourself is, if let's say, like we did with the wall situation, let's say if we assume that, you know, over here mu is 0, so there's no friction, and we over here we say, well, mu is 0, so there's no friction. Well, if I put an object on a ramp on a flat, you know, incline, well, what happens? Especially if there's no friction, if it's really slippery, what's going to occur? Well, the object's going to slide down the ramp. Well, what's making it slide down the ramp? What's making it go down the ramp? Well, what's the thing that pulls everything down? Gravity. But it's not in free fall. Because, you know, the ramp's in the way. But we need to understand that, you know, if we look at the motion of the object is going to move this way. And it could, you know, just be at a constant speed, or it could accelerate, it doesn't matter, but it's going to move down the ramp, you know, along the ramp. And so when this happens, what we like to do in physics is we like to not have a normal coordinate system. We like to make a coordinate system that matches the motion of the object. So what we'll do typically, sorry if there's a little background noise because I'm moving the iPad here, but we like to say that our x direction is either up or down the incline, or the direction of the incline. Now I'm going to make positive x down the incline, but I could make, depending on the situation, I could make positive x up the incline. Doesn't really matter. I can make a positive direction. But let me bring it back down to the other side here. And if that's the case, of course, I hope you realize that that means that the y direction is here, which happens to match the direction of the normal force. And so if I utilize this kind of twisted or rotated coordinate system, well, good news is that the normal force is now along an axis. It's along the y-axis. But the bad news is the gravitation is now in a quadrant. In this particular case, it's in the fourth quadrant. And so that means that the gravity has, according to this coordinate system, this coordinate plane, gravity now has components. And so what we're going to do is redraw. I'll redraw it out of the picture here. Actually, I don't have to redraw it. I can just get rid of the mu. Actually, I'm going to redraw. I'm going to redraw this, and I'm going to make it bigger, and we're going to break this down. We're going to see how and why rotating the coordinate plane is beneficial to analyzing forces in a ramp problem. So I'm going to pause and I'm going to restart the video with a bigger picture of case 2. And the one thing I do want to mention before we go away is that, you know, in all 3 cases, gravity still points straight downward. That's not going to change. That's not, gravity's going to pull straight downward. But what is happening and what you really need to understand is that the normal force, when you're on a horizontal surface, the normal force is obviously going to be maximized. When you're in case 3, when your object is on a vertical surface, basically your normal force approaches 0. That means in case 2, your normal force is going to be somewhere in between. Somewhere between the maximum amount and somewhere between nothing. So that means that your normal force has the ability to change, and that normal force's value will be dependent upon how much angle that ramp is at. If that ramp angle is small, that means you're going to still have a good amount of normal force. If that ramp angle gets really large, that means your normal force is going to really start to degrade. So let's look at how we analyze this. So let me pause and I'll set up a bigger picture.